The distance between Earth and Mars is 34 million miles at its closest. That number sounds manageable until you realize what actually lies inside those 34 million miles. No shield, no soil, no magnetic cocoon, nothing but the raw, merciless physics of open space. And that is where our story begins, with a question that should terrify anyone dreaming of a red planet future. What if the greatest danger of Mars isn't the distance, isn't the cold, isn't even the thin whisper of an atmosphere that can barely hold a breath of air? What if the greatest danger is invisible, silent, and already tearing through every human cell that dares to make the journey? Leonard Susskind, one of the founding architects of string theory and a physicist who has spent his career untangling the strangest behaviors of energy, radiation, and space-time itself, has spent decades explaining a truth that most people never stop to consider. The universe is not empty. It is soaked in radiation. It is a battlefield of charged particles moving at nearly the speed of light, flung outward by dying stars, supernova remnants, and the sun itself. On Earth we live inside a fortress without ever realizing it. Beyond that fortress, in the open dark, that radiation hits you directly. And Mars, unlike Earth, offers no fortress at all. To understand why Mars is such a lethal destination, we have to first understand why Earth is so strangely, almost impossibly safe. Earth possesses two invisible shields working together, and most people don't even know the second one exists. The first is the atmosphere, a blanket of gas 100 kilometers thick that absorbs and scatters incoming radiation before it ever reaches your skin. The second, far more mysterious shield, is the planet's magnetic field, generated deep within Earth's core by the slow churn of molten iron thousands of kilometers below your feet. This magnetic field creates something scientists call the magnetosphere, an invisible force field that deflects charged particles from the sun the way a windshield deflects rain. Without it, the solar wind would strip our atmosphere away entirely, the same way it appears to have stripped away the atmosphere of Mars billions of years ago. That is the first great mystery of Mars, and it is not science fiction, it is established planetary science. Mars once had a magnetic field. Mars once had a thicker atmosphere, flowing rivers, perhaps even oceans. Evidence from dried riverbeds, mineral deposits, and ancient shorelines strongly suggests this. And then, roughly 4 billion years ago, something catastrophic happened. Scientists believe Mars's core cooled and its internal dynamo shut down. Without a magnetic field, the solar wind had nothing to stop it. Charged particles slammed into the Martian atmosphere for billions of years, slowly, relentlessly blasting it away into space, molecule by molecule, until what remained was a thin, fragile wisp, less than 1% as dense as Earth's atmosphere. Mars didn't just lose its climate, it lost its shield. And now, standing on its surface, exposed and unprotected, you are standing on a world stripped bare by the same cosmic forces that could just as easily strip away a human body. This is where the danger becomes personal, and where the physics Susskind has spent his life exploring becomes terrifyingly relevant to something as human as an astronaut's survival. Space is filled with what scientists call galactic cosmic rays, high-energy particles that originate outside our solar system, likely accelerated by the shock waves of ancient supernovae. These aren't ordinary particles. They are atomic nuclei, mostly protons, stripped of their electrons and hurled through the galaxy at speeds close to the speed of light. When one of these particles strikes human tissue, it doesn't simply pass through harmlessly. It tears through DNA strands like a bullet through paper, breaking chemical bonds, shattering the molecular instructions that keep every cell in your body functioning correctly. On Earth, our atmosphere and magnetic field absorb the overwhelming majority of this radiation before it ever reaches us. Astronauts aboard the International Space Station, orbiting at 400 kilometers, are still partially protected because they remain inside Earth's magnetosphere. But a journey to Mars means leaving that protection entirely, drifting through the empty dark for 6 to 9 months, completely exposed. According to data gathered by NASA's Curiosity rover during its own voyage to Mars, an astronaut making the round trip would absorb a radiation dose significantly higher than the career limit set for astronauts working in low Earth orbit. Some estimates suggest the exposure could increase lifetime cancer risk substantially, and that's before even accounting for potential damage to the central nervous system. An emerging area of research suggesting cosmic radiation may impair memory, cognition, and decision-making. Imagine training for years to become the first human to walk on another world, only to have the very journey there compromise the mind you need to survive it. And this is only half of the threat. The sun itself, our life-giving star, becomes an active weapon once you leave Earth's protective shield. Solar flares and coronal mass ejections can hurl enormous bursts of radiation and charge particles into space with almost no warning. On Earth, these events create beautiful auroras as our magnetic field channels the particles toward the poles. In interplanetary space, a major solar storm could deliver a lethal dose of radiation to an unshielded astronaut within hours. This isn't speculation. In 1972, between the Apollo 16 and Apollo 17 missions, one of the most powerful solar storms of the space age erupted. Had astronauts been on the lunar surface or in transit at that exact moment, some scientists believe the radiation dose could have proven fatal. It was quite literally a bullet that missed by months. And on the long road to Mars, there is no telling when the next one might not miss. Now Susskind's expertise becomes crucial to explaining something even stranger, something that reframes the entire danger of Mars in almost philosophical terms. Susskind has spent much of his career studying how information and energy behave under extreme physical conditions, from the edges of black holes to the fabric of space-time itself. One of the most profound lessons from that work is this: the universe does not care about biological convenience. The same fundamental forces that shape galaxies, that bend light around black holes, that determine how particles move through the vacuum of space, are utterly indifferent to whether a fragile carbon-based organism can survive their presence. Mars is not evil. It is not hostile in any conscious sense. It is simply obeying the same laws of physics that govern every corner of the universe, laws that happen to be catastrophically unsuited to unprotected human life. This indifference becomes even clearer when you consider Mars's atmosphere itself. At less than 1% the density of Earth's, the atmospheric pressure on the Martian surface is so low that unprotected human blood would begin to boil, not from heat, but from pressure. This phenomenon, known as ebulism, occurs when the pressure surrounding the body drops below the vapor pressure of bodily fluids, causing them to vaporize at body temperature. It is one of the reasons spacesuits must be pressurized so precisely. A single puncture, a single failure in life support systems, and death would come within seconds. Not from cold, not from suffocation in the traditional sense, but from your own blood turning to vapor inside your veins. And the atmosphere offers no comfort in temperature either. Because Mars's air is so thin, it cannot retain heat the way Earth's atmosphere does. Daytime temperatures near the equator can reach a relatively mild 0 degrees Celsius. But at night, without a thick atmospheric blanket to trap heat, temperatures can plummet to negative 125 degrees Celsius. Imagine a world where the difference between day and night isn't just light and dark, but the difference between tolerable cold and instant, lethal freezing. Every structure, every habitat, every spacesuit would need to survive that temperature swing daily, for years, without a single critical failure. Then there is the dust. Martian dust storms are unlike anything found on Earth. In 2018, a global dust storm engulfed the entire planet, blotting out sunlight so completely that it ended the mission of NASA's Opportunity rover, which had operated for nearly 15 years, far beyond its planned 90-day mission. The storm didn't just block sunlight, it cut off Opportunity's solar power, plunging the rover into cold it could not survive. This wasn't a freak accident. Global dust storms occur roughly every few Martian years, roughly every 3 to 4 Earth years, meaning any human colony would eventually face weeks or months of near-total darkness, with solar power crippled and visibility reduced to almost nothing. Beyond the environmental danger, Martian dust itself poses a chemical threat. Analysis by Mars rovers has revealed that the soil contains perchlorates, chemical compounds that are toxic to the human thyroid, and could contaminate any water extraction or farming systems if not carefully filtered and managed. Even Mars's gravity, only about 38% of Earth's, presents a slow-motion danger that few people consider. On the International Space Station, astronauts in microgravity experience rapid bone density loss and muscle atrophy, conditions that require hours of daily exercise to mitigate. Mars's gravity is stronger than that of the Moon, but still far weaker than Earth's, and scientists don't yet fully understand the long-term effects of living for years under partial gravity. Will human bones adapt, weaken, or degrade unpredictably? Will children, if ever born on Mars, develop skeletal structures suited only to that lower gravity, potentially trapping future generations on a world their bodies could no longer leave? This is one of the great unanswered biological mysteries of interplanetary colonization, and it may prove just as significant as the radiation danger itself. This is where Susskind's broader worldview offers something more than just physics. It offers perspective. Throughout his career, Susskind has emphasized that understanding the universe requires confronting uncomfortable truths rather than convenient assumptions. Black holes challenge physicists to rethink what happens to information at the edge of destruction. Quantum mechanics forced scientists to abandon the comfortable notion that reality behaves the way our intuition expects. Mars, in its own way, forces humanity to confront a similarly uncomfortable truth, that our dream of becoming a multiplanetary species cannot succeed on optimism alone. It requires solving problems as fundamental as shielding human DNA from cosmic radiation, problems that remain unsolved even today. So how might humanity actually survive Mars, if survival is possible at all? Some proposed solutions sound almost like science fiction, yet they are grounded in real engineering research. One idea involves burying habitats beneath several meters of Martian regolith, the loose soil and rock covering the surface, using the planet's own material as a natural radiation shield. Lava tubes, long tunnels formed by ancient volcanic activity and confirmed to exist on Mars through orbital imaging, offer another potential refuge, providing natural overhead protection from both radiation and micrometeorite impacts. Other researchers are exploring advanced spacecraft shielding using hydrogen-rich materials which are more effective at blocking cosmic rays than traditional metals, though the mass required for adequate protection remains a massive engineering and cost challenge. Some have even proposed pharmaceutical countermeasures, drugs that could theoretically help repair radiation-induced DNA damage, though none of these treatments currently exist in a form proven effective for interplanetary travel. And this raises perhaps the most haunting question of all. If Mars requires us to live underground, shielded from the very sky above us, hiding from the radiation, the storms, the temperature extremes, and the toxic dust, what exactly will that Martian life look like? Will future colonists ever walk freely on the surface, feeling sunlight on their skin the way humans have for hundreds of thousands of years? Or will an entire generation grow up knowing Mars only through reinforced windows and rationed excursions in heavy radiation suits? Is that truly colonizing another world? Or is it merely constructing a bunker beneath a beautiful lethal landscape and calling it home? Susskind's life work reminds us that the universe rarely offers convenient answers, only precise ones. The precise answer to why Mars is dangerous isn't a single villain. It isn't just radiation or just the cold or just the toxic soil. It is the absence of the very systems Earth quietly provides every second of every day without asking for gratitude. A magnetic field we never see, an atmosphere we never think about, a gravitational pull perfectly calibrated for the bones and muscles we were born with. Removing even one of these systems creates a crisis. Mars removes almost all of them simultaneously. Perhaps that is the deepest truth hidden inside this red, dust-covered mystery. Mars is not simply a destination waiting for human footprints. It is a test, a physical embodiment of every problem that must be solved before humanity can claim to be a species capable of surviving beyond its home world. And if we cannot yet answer how to protect a human brain from cosmic radiation across a 9-month journey through empty space, then maybe the real question isn't whether we can reach Mars. Maybe the real question is whether we are ready to face what waits for us when we do.